Physics Part 419. An alternating voltage applied across the electrodes causes the crystal to vibrate with a frequency equal to that of the applied voltage. These oscillations are likely to have a small amplitude. However, if the frequency of the applied voltage is equal to the natural frequency of the vibration of the crystal, resonance will occur and the amplitude of the vibration will be a maximum. The dimensions of the crystal can be such that the oscillations are in the ultrasound range of the frequencies greater than about 20 kilohertz. These oscillations will give rise to the ultrasound waves in any medium surrounding the crystal. If a stress is applied to an uncharged quartz, crystal forces involved will alter the position of the positive and negative ions, creating a potential difference across the crystal. Therefore, if an ultrasound wave is incident on the crystal, the pressure variations in the wave will give rise to voltage variation across the crystal. An ultrasound transducer may therefore also be used as detector or receiver. A simplified diagram of the piezoelectric transducer receiver is shown in the figure. A transducer such as this is able to produce and detect ultrasound in the megahertz frequency range, which is typical of the frequency range used in the medical diagnosis. The reflection and the absorption of ultrasound. Ultrasound is a typical of many types of wave in that when it is incident on a boundary between two media, some of the wave power is reflected and some is transmitted. This is illustrated in the figure. For a wave incident intensity, reflected intensity, and the transmitted intensity by conservation of energy. Although for a beam of constant intensity, the sum of the reflected and the transmitted intensities is constant, their relative magnitude depend not only on the angle of the incidence of the beam on the boundary but also on the media themselves. The relative magnitudes are quantified references to the specific acoustic impedance of Z of each of the media. This is defined as the product of the density of the medium and the speed c of the wave in the medium, that is, Z is equal to Pc. For a wave incident normally on boundary between two media having specific acoustic impedance Z1 and Z2, the ratio reflected intensity I to the incident intensity I is given. The ratio is known as the intensity reflection coefficient for the boundary and is given by the symbol as the above equation shows, and it depends on the differences between the specific acoustic impedance of the two media. Some typical values for the specific acoustic impedance are given in the table, together with approximate speed of ultrasound in the medium. If we have air speed 330, the specific acoustic impedance is 430. For blood, it is 1600 to 1.6 into 10 power raised to 6. For bone, it is 4100 to 5.6 into 10 power raised to 6. For fat, it is 1500 to 1.4 into 10 power raised to 6. For muscle, it is 1600 to 1.7 into 10 power raised to 6. For soft tissue, it is 1600 to 1.6 into 10 power raised to 6. For water, it is 1500 to 1.5 into 10 power raised to 6. We got an example. Use data from table. Calculate the intensity reflection coefficient for a parallel beam of the ultrasound incident normally on the boundary between air and soft tissue. Muscle and